So here's a question. How accurate is a LiDAR scanner really? Now this is a question that a few people have asked me, and I've figured it out because I've been scanning for, gosh, 20 years, I guess. And it's something I see quite often. Architects who are commissioning 3D model scanning or LiDAR scanning, and in some cases some surveyors themselves quote accuracies, which you need to be a bit careful about what you say for a number of reasons. First off, the specification is often quoted as plus or minus something millimeters. Now that's straight out of the manufacturer specification, but a few things you need to remember about this. The first is that is just a distance measurement only. That's the time it takes, whichever method they're using, for the signal to go out, come back, time of flight. That's the distance. And that is what's expressed as plus or minus 2, 3, 4, 5 mil. What it's not saying is that point, where is that point in space, horizontally and vertically? Now, the way a scanner works is it rotates and it puts out a number of pulses, and it looks at the rotation of the motor, works out the number of pulses and divides that up, and then gives that as an angle, both vertically and horizontally. However, that's not necessarily where the XYZ coordinates of a point are, because as you get further and further away, of course the separation between the points gets different. So it's really difficult for them to give you a distance because it's all proportional on the distance it is away from the scanner. The other thing to remember is this specification, I see quite a lot of people say, we got it to, half an inch or a tenth of an inch or a couple of millimeters, and you go, well, that, yes, but that specification that you're quoting is for a single scan only. That's just what happens on a single scan. It's not for a number of registered scans, which will then go to be put into a point cloud, the whole of the point cloud. So it's very difficult for you to say plus or minus for 2, 3, 5 millimeters in the whole of a point cloud. It might be there for just one, but not for all of it. The XYZ accuracy of any point depends on, amongst other issues, and we just talked about distance. It also depends on the actual mechanical integrity of the scanner itself, and what we call collimation errors, and we'll talk a bit more about that. It depends on the angle that the LiDAR pulse hits the object it's trying to measure. It depends on surface reflectivity and the noise it will get, and also on vibration and tripod stability. So if you have got a tripod stood next to a pump that's vibrating, you're going to get different variations. Or if you stick it on a pole, on a post, on a height adjustable tripod, you're going to get variations in that. So let's talk about one of the big errors that we can get, and we don't often necessarily know we're getting this until we're processing, and that's what we call a collimation error. So what is a collimation error? Well, if you're a surveyor, you know all about collimation and error because you were taught this surveying 101, how to calibrate your dumpy level by doing a 2-point test, or how you check if your total station's still in collimation by observing an object face left and then turning it around, dumping it, doing it the same object, sighting that face right, and then you look at the difference, and it should be within a certain tolerance. Okay, now we don't have that simplicity of adjustment and checking in the field that you might have with a conventional survey instrument. But collimation arises from a few different things. The main problem we've got is the laser diode, or the source emitting the source for the pulse, is going to be hitting a prism or a mirror, and the angle and the offset that hits is really important. I'll show you a diagram in a minute. Then we've got the basic laws of optics of reflection. You might remember this from your school days. The angle of reflection is twice the angle of rotation of a surface, of the mirrored surface. But the problem with these, and what we call with the emitter, is not exactly on the rotational axis of what we're doing. We can get both an offset error and a step error, and generally a mixture of both. Well, what does that mean? Well, what we actually get is a warping of data. We're not getting the true horizontal and vertical. The distance might be perfect, but the horizontal and vertical angles we're getting and projecting out might vary. And we see this as a wave error, or in the worst case, a step error. And you might well have seen this on a some scanners where you look at the image of the scan and you've got a weird step in it. That step is a collimation error. So why does that occur? Well, okay, if we have a look at these two drawings here, so the angular error, let's just talk about the angular error. Okay, so what I've got here is a light path. Now, this would probably be the other way around or side to side, but we've got a light path coming from our laser diode emitted down here. And if this is coming in at 90 degrees or 45 degrees, this will be at 90. Obviously, going back to our days at school. Right, that's fair enough. However, if the axis of rotation is slightly different, if the angle of the light is at slightly a different angle, then what we're going to get is this change here. So we'll get an angular error here and an angular error here, which actually produces a cone, not a 90 degree. Okay. Now, if this moves at any time, okay, or if this surface moves at any time because it's not accurately set, then we'll get this coned error. And this is a cone error for every single point that we get going around. Okay, right, and the problem with that is we get little bits of displacement. So angular error, we've got that. The next one though is a bit more dramatic, and this is what we call a step error. So a step error, the light path comes in. So this is the axis of rotation. So the mirror or prism is spinning around this point here. So if the light path comes in and goes out, providing this mirror and this point here is not moving relative to the light path, it's going to come out at 90 degrees perfectly. All right. However, if this mirror that's rotating slightly out of axis and is on its rotational axis and the light path isn't hitting that, what we will then get is this. So at this point, it's there, comes out here, and as we rotate it 180 degrees, it comes out here. This red line here is the step error. Okay, and the step error is going to be the distance, at least the distance that's off. So what we will get is this step error plus an angular error. And it's very rare to find one or other. Quite often it's both. And the problem with that is then we start getting errors in our points because they're not on the correct X, Y, and Z. Sorry, they're not on the correct horizontal and vertical angles. We're looking at vectors, so it's a horizontal angle and a vertical angle, and the distance down now defines the point in space we're getting the return signal from. Make sense? Okay, so what that means is that if there is any error in the mechanical center or if the diode moves slightly in its housing, then you will get an error that's going to be either an offset error or an angular error, or more likely a combination of both. Angular and offset errors for your H and your Z readings, so your horizontal and vertical readings. Okay, so you could get that right, but there are other things as well. So you can get things like moisture on the mirror, which will cause another refraction. The stability of the tripod, I think we mentioned that, machinery vibration, and then you get the normal effects we get from a total station if we're using it, atmospheric or scintillation effects as refracts to a different density. Now, in surveying, quite often that's not too bad because we're shooting through, but if we're shooting vertically, we can be going up through different temperature ranges and different refractions, and you'll get different errors. Okay. You've also got the ppm corrections that you put into a total station, as you know from surveying. Temperature, barometric pressure, speeds up or slows down the speed of light. And then the point is, how straight is a light beam? Well, light beams do what we call scintillate as they pass through different temperatures, different moistures. You do get refraction, so the thing can be moving. And then there's the other thing to do with the level and compensator accuracy. How level is this thing? You don't know. Really, you're just taking it on trust till such time it doesn't really work. So what's the issue with this? Well, okay, now most people will quote their accuracy based on a quality report that is given, and same applies actually in photogrammetry software and in point cloud registration, but the common thing they call is a RMSE, root mean square. However, just to state, this is actually a measure of the state of a mathematical process using the data available. Okay, if the data is wrong because you've got a calibration error, then you're going to get a false sense of accuracy anyway, and there are a few other issues that go along with that. It's not, RMSE is not strictly a measure of the accuracy of the geometric model that you're producing. It's an accuracy of the maths, which may be a subtle distinction, but if it's making assumptions on the data, okay, then the data's wrong, then strikes me that the accuracy is going to be wrong too. Right, so how does this impact us? Well, basically this, when you've got a collimation error, the first opportunity, because you can't field check it very well, is in any cloud-to-cloud registration, it won't work, especially if you change the orientation of the scanner. So if I'm keeping the orientation north-south or things, and then it should iron it out in theory, but actually if you turn it round every so often, then you'll get the collimation error. And you will see that the point cloud isn't looking at the same point cloud. It's just not common. The points it's trying to compare in planes and in edges are not in the same place. So you're going to get some error, and sometimes it just fails completely. Now it may work if you keep the orientation the same north and south, but you'll give you a false sense of confidence in the accuracy because it's warping warp data together. All right. But because the position is moving, you'll still see some error and some different things, some weird effects going on in the point cloud. And the other thing to bear in mind is the further away the object, the bigger the potential error. If I've got a collimation error and on the vertical and horizontal angles, obviously the further away I go, the bigger the error is going to be if I'm trying to observe a common point, an edge, corner of a building, whatever it might be. Okay, so what can we do about this? Well, there are some things you can do to check that everything's working okay. For example, you can do a visual check on the point cloud, and that's why many of us who do point clouds are always doing sections and cutting sections through the point cloud so we can see if we have noise, if we have surface ghosting and multiple layers where a floor or a roof or a wall should be. We see 3 or 4 different examples of it. I particularly myself always look at the vertical control, especially when you're working outside, because inside you've got floors and things. Outside it's really difficult sometimes to get a plane which is a true plane that's level. Very few things are absolutely flat outside. You'll get discontinuity of surfaces, so lines will suddenly break halfway through, or particularly you'll see this on as you're shooting up vertically, things become pretty obvious that you've got a collimation error. But the other way you can look at that is if you are using survey control points, you can look at the delta values in all 3 axes, X, Y, and Z. And you're particularly going to see it in vertical shots above you, steep vertical shots as well. Just the same way as you would do if you were shooting a total station. Sometimes you have to do face left and face right. And halve that error, especially on particularly steep sites, because although we've got vertical index control, we still need as good practice to check it. And the point of this is suggesting, if you were thinking about it, we're actually survey control points are pretty damn fundamental to the accuracy of that. And for those of us who do lots and lots of these things, we will probably, most of us I would suggest, is we will use survey control as well. So the point of buying a scanner by itself and expecting to hit those accuracies, what you should be buying is a total station and a Travis kit as well at the same time, because that's the only way to validate this, apart from visual sectioning of taking sections through the point cloud, and that means vertical sections and horizontal sections too, so you can see if there's any ghosting. Now, some of the ghosting will come from natural things, reflection of the material, slight deviations, vibrations and things like that, but we're trying to model from this and produce accurate captured reality or capturing geometry with these LiDAR scanners. Okay, so there's a few things you should be doing, okay, to check if you've got this. First off, look after your scanner. Okay, some of them are more susceptible to bumps than others. Hand hold it, hand carry it, try and keep it as carry-on baggage if you can. Keep an eye on it, okay. Also, what you should, as good practice, is change the orientation of your scanner between scans, okay, which is the rough equivalent of face left and face right that you would do if you were using a total station. If you want to check for any collimation or ever that. Other one is, when in doubt, or all the time, use survey control. Now, the state of survey control, how much survey control you put in, is entirely up to you, but most of us who are surveyors would give you an idea of what it is. Some scanners less than others. Some other scanners, you've got to do a lot of it. because you can't fix the collimation error yourself. There's no way of field adjusting these. It has to go back to the workshop if you've got it. And bear in mind, as soon as that certificate of conformance, because it's not a calibration certificate from a metrology point of view tells you what the error is at every point on that circle, horizontal and vertical. Okay, all you get from most laser scanner manufacturers is a certificate of conformance to their specification, which is for a single scan. Okay, how accurate is your laser scanner really? Well, it's as accurate as your physical checks and your QA and your survey control, because most of them use let's get it out of the way, excuse me, I've done that wrong. Most of the registrations use plane and edge detection to do that, and that's great. Personally, I would always prefer to use a voxel based registration software than plane and edge, because then I know I'm getting more accurate measurements. And there's a few systems, or only 2 or 3 systems, who actually use that. If you want to know what they are, drop me a line, I'll tell you. But in the meantime, just make sure that you are actually giving the right level of accuracy to your client. And if you are a client commissioning these surveys, please note that you actually need to get some form of documentation in the form of survey control deltas to actually confirm how accurate they are. Okay, that's it. Laser scanners, how accurate are they really? Pretty damn good, providing you look after them and you know what you're doing.